Okay, we are ready for the last lecture of Dominik. So please, Dominik, carry on. Thank you.
Okay, welcome back, everybody. Thanks for sticking around. So today I want to talk about something which I introduced yesterday, namely the first threshold problem. So yesterday we finished proof of the Nash-Kuiper theorem. We saw that we have flexibility in C1, and I reminded you that we have problems with isometric embeddings into low codimension Euclidean space, which are regular. Problems with isometric embeddings which are regular into Euclidean space of low codimension. Sometimes we don't have existence, and sometimes we do have uniqueness, like in the Weyl problem. And so this gives, or the comparison or the analogy to what happens in fluid dynamics and Onsager's conjecture kind of motivated us to ask these questions about a regularity threshold, like regularity thresholds dividing these contrasting behaviors. And so our setting was we take a closed two-dimensional smooth manifold and metric on it with positive Gaussian curvature. Say smooth. And the question is, does there exist a Hölder threshold, as I said, motivated by the Onsager conjecture, such that we have flexibility in the sense of Nash-Kuiper below, so alpha less than alpha 0, then Nash-Kuiper holds in C1 alpha. So what I mean by this is every short map from this two-dimensional manifold into R3 can be rigidity holds in C1 alpha, or a bit more precise, rigidity holds for isometric embeddings, which are dysregular. Meaning, if you give me two isometric embeddings from this two-dimensional manifold with positive Gaussian curvature into R3, which are both C1 alpha for alpha regular and big enough, then they have to be the same up to translation notation. Okay, so that's the threshold problem. I stated another threshold problem saying, okay, this problem is quite hard, and if we got to it by analogy with fluid dynamics and Onsager conjecture. But then if you look closely, Onsager conjecture is somewhat weaker, because we're not saying that there is a threshold such that weak solutions which are more regular, they're completely classified, and weak solutions below, they might be completely wild. But in Onsager, we're saying that there's a threshold such that weak solutions which are more regular than this threshold, they satisfy an extra identity, the energy identity, whereas below, we might violate this extra identity. And then we came to the second threshold problem, which kind of says, okay, there is a threshold, or we asked if there is a threshold such that below we are flexible in this generalized sense, namely that we can violate an extra identity, whereas above the threshold, we must satisfy this extra identity. And today, we want to talk about this first threshold problem, tell you what is known, and tell you a bit, how one might think about it, and mainly about this first part over here, namely the flexibility. Nash-Kuiper theorem holds. Because now that we know the construction of Nash, I just want to show you how you can tweak this construction to get more regular embeddings over here. But let me first give you the results, or what we know today about this threshold problem. And I should say, so all of the results concerning the flexibility, they come from, no, let me not say this, but give you the results. So I think it was crucial. Yeah, results. Okay, so C1 alpha embeddings, the first who started to think about C1 alpha embeddings was actually Borisov. And in the 50s, Borisov showed that the rigidity theorem over here holds if alpha is bigger than 2/3. So Borisov, first theorem, which is Borisov in 58, where I mean, in a series of very geometric papers, like 4 papers, he showed that he showed that the rigidity theorem holds in C1 alpha, alpha bigger than 2/3. So let me state this: if alpha bigger than 2/3, rigidity 1 alpha, again over 2-dimensional closed positive Gaussian curvature, isometric embeddings into R. And he builds off, I mean, it's a series of very geometric papers, 4 papers, and then he still uses results of Pogorelov about the rigidity of convex surfaces. And okay, I should add over here, so very geometric paper, there's a different proof of the same result. I mean, the same result Borisov gets, and then using the results by Pogorelov, you can conclude the rigidity. And this is in a more recent paper by Dominik, Leibniz, and Sekelididi, 2012, I think. So this is an alternative proof of the theorem, which is a very short 2 pages PDE type proof. This is geometry. It's pieces. So this is rigidity, and this is unfortunately still the state of the art. We have some results which seem to suggest that you could lower this to 1/2, maybe, if you're very smart. But at the moment, we're still at 2/3. So if you have 2 isometric embeddings of a positively curved closed 2-dimensional manifold into R3, which are C1 alpha, alpha bigger than 2/3, then they are the same up to rotation translation. Okay, and for flexibility, so this is rigidity, and the story is done. Flexibility also, it was also Borisov who was interested in this question, and in 1965, he stated the following theorem. Theorem, and I put it in quotation marks because he didn't give a proof. So this is also Borisov in 65. And what Borisov said is that you should expect the Nash-Pfeffer theorem to hold in C1 alpha. So Nash-Pfeffer theorem holds in C1 alpha Mn R n plus 1 for any alpha less than 1 over 1 plus n times n plus 1. This is called the Borisov exponent. Borisov's exponent. So what he's saying is a compact manifold, n-dimensional. You have a short map into Rn plus 1. In an arbitrarily small neighborhood around this short map, there is an isometric map of this regularity, C1 alpha, any alpha between lower than this number over here. What he also says, so if you plug 2 in here, you see 1 over 1 plus 2 times 3 is 1 over 7. So 2-dimensional, we should expect 1 over 7, but Borisov also already says in 1965 that you could do better for 2D. If n is 2 alpha less than 1 over 5 should work. And as I said, Borisov didn't give a proof, so he gave a proof 40 years later. So proof in 2004 in the case 2D, where n equals 2 analytic method and alpha less than 1 over 13. That's what he proved in 2005, 4. And in this paper, I stated over here, Conti Delele Seglihidi, they show in 2012 that actually this claim is true. Well, let me state it over here, theorem. And let me abbreviate Conti Delele Seglihidi. Borisov's claims are true. If you're in the same situation as we were for our simplified Nash, namely the manifold is simply one chart. So Mn is an n-dimensional ball. And in general, you can get an exponent, but you get it slightly worse. So you need to do a covering argument, which kind of, so the exponent gets worse because you need more spirals, basically. For general compact, and okay, I should say Borisov's claims are true, this part. So the n equals 2, they don't show. For general compact and n alpha less than 1 over 1 plus n times n plus 1 squared is fine. This second part over here, this is just, you do a construction locally, you get a nice exponent. And then if you have a compact manifold, you do a smart covering, and then you run the process on like disjoint coordinate charts, you run the process at the same time, but then you have some overlaps. And these overlaps kind of have the effect that your exponent gets worse. But if, so then in a result, very recent result, by Laszlo and his postdoc Mintal Sam. So theorem about the 2022. They show that actually you can do covering much more in a smarter way than just doing one patch and then do a covering of patches and run the process simultaneously. But yeah, a more difficult process over here allows you to get the same exponent over here for general compact. So alpha 1 plus m times n plus 2, 1, 2 for general compact. So basically, this theorem shows you that whenever you can get an exponent for the local case, so when you're an n-dimensional ball, you can also get it for the general compact manifold. Okay, and this is for general n. What Borisov also said is that if n is equal to 2, you should get 1 over 5. And this is actually how I got into this business. So this was my master thesis over there. Still there is. And myself and Laszlo, 2015, published in 2018. So alpha less than 1 over 5. Okay, with n is equal to 2, and n isn't. It's just a disk in our. And then, okay, with this work, you see that 1 over 5 is okay for general two-dimensional compact. So Borisov's claims are true over there. And this was the state of the art for a very long time. And now this I'm pretty excited about. This is the result by Tao, myself, and Jonas Hirsch in Leipzig. This is on the archive since 1 week. So, okay, I should maybe say something over here. We had this result in 2015, and as I said, look at this question over here. It came as an analog of the Onsager conjecture in fluid mechanics, and because of the similarities in the proofs, or in the strategies, or in the techniques involved in the proofs, and also of the statements, there was hope that progress in one problem would lead to progress in another problem, like progress here would lead to progress in Onsager, and vice versa. But then Onsager was solved in 2017, and we were stuck over here for a long time. So that's when we started thinking about a closer analog to Onsager's conjecture with the threshold problem 2 I gave you yesterday. So we were at this threshold for a long time, and now finally, last week on the archive, we have that alpha less than 1 over 1 plus new exponent n times n minus 1. Okay. So we get slightly better than Borisov's exponent. In particular, for n equals 2, you get the 1 over 3. So Onsager's conjecture basically for the isometric. So this we do it locally, but then again you can somehow. We don't do this in the paper because it just adds a lot more technical pieces which somehow obscure the main idea over here. But I 100% believe that this is true for general complex n-dimensional manifolds. Okay, so let me summarize. State of the art for this problem is rigidity below 1/3, rigidity above 2/3, flexibility in the sense of Nash-Kuiper below 1/3, the 2-dimensional.
Sorry, Dominik, I mean, when you state stuff over there, it's always 2, and over here it's become n.
Exactly. So this is general L. All this flexibility is for general N.
Oh, okay. So
and then we apply it to the 2-dimensional case over there. Okay. Because the threshold problem, I somehow want to have a statement where the flexibility applies to the same objects, namely these 2-dimensional positively curved manifolds as the rigidity statement. But the flexibility statement over here we get as a special case from the more general flexibility. No. Okay, so flexibility really means Nash-Kuiper theorem holds, and then for the various manifolds. So no curvature assumptions on G of them. This is just needed for the rigidity. Okay, so summary of our threshold problem, bless you. Summary. So alpha between 0 and 1 over 3 through Nash-Kuiper. Alpha between 1 2 over 3 rigidity. And between, so 1/3. No idea. So in the following, my goal is to show you, first of all, why one should hope to get C1 alpha isometric embeddings, why Borisov thought that this is the right exponent, and kind of give you a heuristic explanation on how this exponent, or how you could prove such an exponent. And then somehow hint to how you could think of why it should be better for n equal 2, and what you can do, or how to get better exponents than this. Any questions at this point? I know it's not too precisely stated, but I hope it's. So, to me, why there is hope? And I should say all of these results over here are generalizations of Nash's iteration speed. So all of these results, all of these guys, I mean, I'm trying to prove Nash-Kuiper. I'm trying to prove that around any short map there is an isometric map of a given regularity. And I'm constructing these maps as a limit of short maps, which are Cauchy in the right space. And so because of this, let's go back to Nash and see what we can do. So recall Nash. What we are doing is we are adding oscillations or perturbations of this form A over lambda sine lambda x dot eta. And the cosine piece. And we saw that if we choose lambda large enough, this guy is close to u in C1. Its induced metric increases by this primitive metric a squared eta tensor eta up to a small error, which I can make very small by choosing lambda large enough. And just choosing lambda large enough, I get a sequence converging in C1 to an isometric embedding. So observe, we saw that dv minus du can be bounded by, so that the largest term in the derivatives is when the derivative is sine or cosine. Lambda pops out, cancels this lambda, I see an a. And the a came from the decomposition, so I had that g minus u is decomposed in the primitive matrix, eta tensor eta, basically. So a is like the square root of g minus u. And we saw that we can somehow choose our parameters such that this along the sequence goes to 0 in a summable way, or geometrically. 0 geometrically. And so we get a C1 convergence of our sequence. Now, if you want a C1 alpha regularity of your limit map, you should start looking at C1 alpha norms of this construction. Actually, it's a bit easier, technically, to just look at what the second derivative is doing. So, as to the question yesterday, what goes wrong for C2? If you look at second derivatives, you can see that these blow up. So first derivatives, they converge. Second derivatives blow up, because what happens if I take another derivative? On the other hand, so if I compare second derivatives, the dv squared minus u squared. Again, the biggest part is, or the biggest term is when the derivative hits another times the sine or the cosine, because then I get another lambda out. Lambda is very large. So you can see that the second derivative is the largest when I get two derivatives on sine. Then I see a lambda squared divided by lambda times a. So roughly, I see an a times a lambda. And I said a couple of times, certainly 10 times or so yesterday in the proof, just choose lambda large enough. Choose lambda large enough. And this means that this guy is going to plus infinity. So lambda large enough, this goes to plus infinity, but this guy goes to 0. A goes to 0. So a goes to 0 because it's induced metric, square root, and I'm converging. Lambda goes to plus infinity, but you see there is a fight. So you might hope that if you're not looking at lambda, but lambda to some small power, then maybe the a wins. So the hope is the following. Hope is that a0 lambda to the alpha is going to 0. For alpha small enough. Just choosing lambda large enough, but then if I put a very small power over here, you might hope that this guy wins. And now what is alpha 0 times lambda to the alpha? What is a0 times lambda to the alpha? It's exactly the C alpha norm of the derivative. So, but dv minus du, or let me say this like this, but alpha 0 lambda to the alpha is roughly speaking the C alpha norm of the difference. If you look at the function like the sine of lambda times something, if you take the Hölder norm, the alpha Hölder norm, you exactly get a lambda to the alpha out. I will make this more precise later. So you might hope alpha small enough, this guy converges to 0, but this should mean that my sequence converges in C1 alpha, or the derivatives can converge in C0 alpha. This means that the sequence converges in C1 alpha. And so now here is our hope, and you see our task is to be able to say something like this. I have to be a bit more careful than saying choose lambda large enough. Choose lambda large enough. What I want is to choose lambda sufficiently large, but as small as possible. Because if lambda is as small as possible, this alpha can be chosen as large as I want. Using a slower increase of lambda will give me a larger alpha such that this still converges. So the task over here is choose lambda systematically. And systematically as large as needed, but as small as possible. Because then my sequence or the C2 norms, they blow up very slowly. If I choose them as small as possible, C2 norms blow up slowly. So then the right power over there should give me a convergence in C1. Okay, so what do we need to do? Choose lambda systematically where, well, then we have to analyze the terms where we chose lambda large enough. So remember, so where we said choose lambda large enough was in these terms, which I just called O1 over lambda. And I just said, well, there is a 1 over lambda in front. I choose lambda large enough such that this is as small as I want. Now I really need to see what these terms are. And then depending on what these terms are, I can say I need lambda exactly this large. And if you do this, you run into a first problem. So analyze 1 over lambda. This leads you to the quantitative step. It's the following. So I'm trying to give you some details, but trying to be as non-technical as possible. So something will just come out of the blue, something will be a bit more precise. Here I'm stating this a bit more precisely just for you to see what the problems are. We're not proving this, but let me just state this. So quantitative step means I do this. This is what Nash called a step, just adding one spiral. Now I need to analyze what happens to the derivatives over here, or actually really precisely estimate this guy, and precisely estimate the error in the induced metric, so that in the end I can say, oh, I have to choose lambda exactly so large. So the quantitative step is the following. Again, everything very heuristic. So lemma. So we take our ansatz. So that's cosine under x dot theta psi. This is our ansatz. Where, okay, C infinity, this is very large. This is a unit vector. These two are orthogonal as usual. So then dvt dv is dut dv plus the induced metric plus some error, which before I just called O1 over lambda. And now I really need to estimate what this error is. Because in the end, I want to choose lambda large enough such that in absolute values, it's smaller than something. Yesterday I wanted it to be less than delta. Okay, but now if you go, this just means you compute the derivative, you compute all the terms, and then you estimate these terms. All of them have a 1 over lambda in front. So up to a constant which only depends on n and g. So I have a term which has a 1 over lambda in front. I think I get A0 and the derivative of A. And then I get a term, the most important term, which has an A0 in front and a second derivative of U. This is kind of when my derivative, so I have to compute the derivative of V. The derivative of V can also hit the zeta or the psi, the normal vector fields to U. And you can imagine normal vector fields to U, they're somehow built out of first derivatives of U. So second or first derivatives of the normal fields are like the second derivative of U. So this term here corresponds to the term where the derivative of U hits the term when the derivative is over here. That's the crucial term over here. And then you get other terms, the lambda squared, I don't remember exactly. Because I imagine lambda to be large, these will be smaller than this one.
Is that a lambda trip? So it's A0 times, A0 times D, A0. Okay. Not A0 times D U0. Okay, sorry, that's why.
This is a term where.
Yeah, no, that's fine. I just read that as U0 and then I was like, that feels mismatched.
No, this is A.
Yeah, okay.
This is like.
Yeah, sure. No.
Over here.
Yeah.
Okay, so this is one quantitative estimate where now we can say, okay, if we want to achieve a certain size of the error, just look at all the terms, how big these are, and choose lambda exactly these guys divided by, or the thing we want to achieve divided by the size of these guys. A second point where we wanted to see how big lambda has to be is we wanted to estimate this one. So let's try to see. In fact, this is and. So B minus U. Not sure, so I don't want to introduce too much notation. Let's just say the kth derivative of V minus the kth derivative of U can be bounded by a constant. Okay, these depend on K, N, and G. And then I have a couple of terms, namely, when the derivative always hits the sign, I get a lambda out, K times, and I have a 1 over lambda, which cancels 1. So the biggest term is always when the derivative hits the fastly oscillating guy. I get the lambda out, it cancels 1. So if I take K derivatives, I should see a lambda K minus 1, and then I see A 0. Okay, you can make this precise. You can make this precise using interpolation estimates and okay, Leibniz rule and so on. So meaning so technically, if you compute kth derivative, you have to compute all the different combinations. Let's say L derivatives fall on A, M derivatives fall on here, and S derivatives fall on here, and the sum is K. So a kth derivative of a product like this is just some derivatives on here, some derivatives on here, and some derivatives on here, and the total number of derivatives is K. And in the estimates using interpolation estimates, you can see that you can always estimate these terms just by saying, I put all derivatives on here, I put all derivatives on here, or I put all derivatives on here. And these guys, when I do this, I have no derivative on here because I've put all of the derivatives on this guy already here. So all derivatives on here will give me a lambda to the minus 1 dk on A. And then all derivatives on this guy will give me a k plus 1 derivative of U plus A0 and dk plus 1 G. And the proof is an exercise using computation, Leibniz rules, and interpolation estimates. I might just put these in the in the notes if you're curious. But basically what I'm referring to is a formula if I want to compute the k derivative of the product of functions, I can estimate this by a constant which depends on k. And then the k derivative of f times the zero derivative of g plus the k derivative on g plus the zero derivative on f. I don't need to care about intermediate, I don't need to care about when I derivatives fall on f and k minus I fall on g. Because technically, if you do just the usual Leibniz rule, you get these terms, but you can always estimate them from above by just putting all of them on f, none on g, and all of them on g, none on. So this is what goes into this estimate. So why I'm stating this estimate is to show you the following. So what happens over here? And this is our problem. So I said, okay, let's choose lambda systematically. Choosing lambda systematically as large as needed, but as small as possible, means we have to analyze this error term. Okay, we analyze the error term. So we see that if we want to get a certain decrease in the error, we have to look at how big these pieces over here are and choose the lambda exactly so large, such that this whole thing is as small as possible. But so you see that if you want to achieve a certain decrease, you need to choose lambda depending on the second derivative of u. And now imagine we're doing this a couple of times, right? We did this n times in a stage. So I have this one. I get my first error. I choose lambda so large depending on the second derivative of u, such that this error is small. Okay. I go one step further. Instead of u over here, I put my v, and I get the new map w. And I want to choose lambda for this new w large. If I go to the formula, I see I need information on the second derivative of v now. But what is the second derivative of v? But I go down here and I see I get information on the second derivative of v by looking k equals 2. And you see I need information on the third derivative of v, because two derivatives could follow on the normal vector over here. So I need information, so to choose lambda in the second spiral, I need information on the second derivative of b. For information on the second derivative of b, I need information on the third derivative of u. And so if I go on to w here, I get a u embedding. I need information on the second derivative of w, needs information on the third derivative of b, needs information on the fourth derivative of u. So what's happening is that I'm losing information about derivatives. So I need all information on all of the derivatives of u, basically, because then I have my n. So in the iteration, what's happening is I do this, I add n spirals at every stage, but then I'm repeating this infinitely many times. So this means that I would need information on all of the derivatives of the map which I started from. Quantitative information. And this is actually, so this problem is common, or is also, this problem we call the loss of derivatives. It's actually not loss of derivatives, but more loss of information about derivatives. Because I'm doing an infinite sequence, this is really a problem. So where am I? Loss of derivatives. So to compute, choose lambda, I need info on into u. To choose the next lambda, I need info on p2, which needs info on discrete u, and so on. So need input on all derivatives. I need quantitative info on all derivatives of result. And Borisov overcame this problem in his proof in 2004 by assuming that we're starting with something analytic, because then you have control on all of the derivatives. So Borisov 2004, if G is analytic and U0 is analytic, fine. And actually, this problem of loss of derivatives also appeared in Nash's 56 paper. And Nash dealt with this problem by introducing a smoothing step. So instead of looking at my map UK, so I want to build UK plus 1 from UK, what you can do is, instead of looking at UK, just mollify this map at a certain length scale. So think about my map looks somehow wiggly. What I do is I somehow, the highest frequencies, I just smooth them out. So I have a bit, I mean, my canvas is a bit whiter. So my canvas is a bit whiter, and what I can do is very systematically put back in the high oscillations. So I have a map UK, which maybe has high frequency oscillations, but the very high ones, I just smooth them out, and then I put them back in with this lambda, but very systematically. So first of all, I clean the high oscillations up, and then I'm putting them back in. And okay, analytically, the modification allows me to estimate all of these derivatives over here just by the modification parameter. So what you need to do is choose a nice, modification parameter with, smooth this map out at a length scale which is small enough but not too small. So, and that's what De La Lisse and Zerlini and Conti did. So you see as use modification. Like in Nash 56. Or almost like, Nash 56, it's a bit more difficult. Okay. So if you do this, so I just wanted to state this one explicitly to show you that there is a problem with the loss of derivatives. But now let's assume this following heuristic. Let me not go too much into this modification detail over here, but let me assume that we could, and this is what, you can make this precise by using modification. But for the moment, let's simply assume that this perturbation over here gives me the following heuristic. So now, let's assume the following heuristic. Which is if lambda large enough, then you can throw away most of these terms because they are smaller. And the main term in the error is exactly this one. So if you do this perturbation, you get an error in the induced metric, or you get the increase of the induced metric by this primitive matrix plus an error, which you can estimate by a constant A0 and then the second derivative of B divided by lambda and EKV minus EKU less than or equal to constant depending on K lambda K minus 1 and then A. These are the big terms. These are the big terms if lambda is large enough. And this can be made precise. Shown to be true. Using modification. So you see that the error somehow, okay, before I just said this is over 1 over lambda, I choose lambda large enough such that this is small. Now I see that I need to choose lambda depending on the second derivative of u. And I see how much the second derivative is growing, namely the second derivative of v is exactly lambda times a. So for the next one, I see that I need to choose lambda. The next lambda, I need to choose it larger than the previous lambda, because the previous lambda is the second derivative. So let's see how this over here would give you something in the stage proposition which we had yesterday. So applying two-stage proposition. So assume you're given UK. Think about U as being the UK. I want to construct B want. Okay, and now I need to be a bit more precise, or let me just. So this A over here, it came from decomposition, and I saw that its size is like the square root of the distance between the induced metric of U and G. And let me call this distance delta, strictly short. Note. So delta is this size, it's small, but it's positive because I'm strictly short. Just to save some space. Okay, want B, which was the UK plus 1, strictly short. Such that I decrease this guy by some factor. Yesterday we said, okay, let's decrease it by half. Such that, let me write over here because I don't know, I have the heuristics over there. Strictly short, such that the induced metric decreases by a factor k, 1 over k, for some large k. Yesterday, in the proof of the theorem, we had k equals 2. And what we had yesterday in the stage proposition is that, or we said that given a short map, given any small number over here, I can construct V just by choosing all the lambdas large enough such that I'm satisfying this. So now let me see how large I need to choose the lambdas by using this heuristic. The strategy before is the same as before. Stage proposition means I first decompose this guy, or like minus something because I want to stay short. So first decompose D minus U star E minus, and I subtracted yesterday, I subtracted delta halves. Now I'm subtracting delta K identity, and I'm assuming, okay, delta is small enough. So K I think yesterday I called it I, A squared, I, beta I. 1 to some number big N. And now I'm adding back the spirals. So secondly, add spirals. So I'm doing U0 is U, and UI is UI minus 1 plus AI divided by lambda I sine lambda I x dot theta I zeta I plus the cosine piece for lambda I to be chosen, and set D to be the last one, UN. Now let's see how we have to choose these lambda i's to get this decrease of the metric error. by quantitative stage, and by quantitative step, we have that for every I, induced metric is simply the old one, plus this primitive metric, every I squared theta I, plus the error with EI can be estimated by a constant, and then AI, second derivative of UI minus 1 divided by lambda I. And okay, AI comes from this decomposition over here. It's like the square root of this one. And this one is delta. So AI is like delta square root. Let me forget about the constant and simply write this inequality. Square root, so AI, and then the second derivative of UI minus 1 divided by lambda. Okay, so let's do this iteratively and look at the first guy. So E1 in particular. So choose lambda I so large that EI, every EI is less than or equal to delta over, okay, maybe let's do delta over 2k over here. Then we'll do 2 and then big N, k, n. So that in the end, G minus the induced metric less than or equal to let's do delta over 2k plus the sum of all the EIs, which is less than or equal to the sum of 1 to n, less than or equal to delta over 2. So that's my strategy, just choose lambda I at the ith step so small, so large that the error at the ith step is smaller than this one. So that in the end, when I'm summing, I get something which is very small. This delta over 2k comes from this one. Okay, but it's exactly the same computation as before. The induced metric of V is the induced metric of U plus all these pieces, which are nothing else than this one. And yeah, it's the same computation. So in particular, since E1 is less than or equal to delta 1/2 and the second derivative of U divided by lambda 1. I know how I want to choose lambda 1 because, okay, this is U0, which was my max U0. So choose lambda I to be, I divide by this, so I want delta V squared of U. 0 divided by delta 1/2, and then k, or 2kn. Let's just write k. So that when I'm dividing by lambda 1, the second derivative over here cancels. I get another delta 1/2, which gives me a full delta, and I get divided by k. Okay, that's my first delta. And for the second one, I go here. I see the second one is like where I have it here. The second one is this delta 1/2, and then second derivative of U1 divided by lambda 2. Second derivative of U1, I need to go here and see, okay, what's the second derivative of U1? It's exactly lambda 1 times A. So on the other hand, to compute E2, I need information on the second derivative of U1. Second derivative of U1, I get information from here. So second derivative of U1 less than or equal to the distance and difference. plus second derivative of u0. And just using the heuristic, I see that this one is less than or equal to a, which was delta 1/2 from the decomposition, and I see the lambda 1 popping up. I see that this is delta 1/2 lambda 1, and then plus the second derivative of u0. But the second derivative of u0 is delta 1/2 lambda 1 divided by k. In particular, it's much smaller than this one. Second derivative of u0, it's over here. It's the same as lambda 1 times square root of delta divided by k. So it's certainly smaller than square root of delta times lambda. Let me write this. It's delta 1 lambda 1 divided by k. So this is to say that in total this is less or equal to delta 1/2 lambda 1 up to constant. So when I want to compute E2 or see how large E2 is, I see it's delta 1/2 second derivative of U1. Second derivative of U1 is delta 1/2 lambda 1, and I divide by the second frequency, lambda 2. So I see that the previous frequency pops up in the denominator. All right, so we're almost done over here. So, E2 less than, by the heuristic, this is less than or equal to A2. All right, I have it here, it's less than or equal to the delta 1/2 second derivative of U1 divided by lambda 2. This is from here, from the heuristic. Second derivative of U1, I go down here and see I estimate it to be delta 1/2 lambda 1. So this is delta lambda 1 divided by lambda 2. And the same thing happens if you compute now the second derivative of U2, it will be estimated by delta 1/2 lambda 2. Second derivatives of UK, delta 1/2 lambda k. And so the correspondent error, you always see lambda k divided by lambda k plus 1. So in particular, I choose lambda 2 simply to be lambda 1 times k. And going on, choose lambda I to be lambda I minus 1 times k. And this is the same as the first one. So this one, as 0 divided by delta 1/2, and then k to the I. So this is how large I have to choose my frequencies to get the decrease which I want. And the second derivative of ui less than or equal to delta 1/2 lambda I. Right, so ui is constructed by adding a spiral of frequency lambda I with amplitude which is delta 1/2. I should see the lambda I popping up. So in particular, my B satisfies, so with this choice, we get G minus V induced metric less than or equal to delta times divided by K. And the second derivative grows, and I'm interested in how fast the second derivative grows. Well, the second derivative over here is like delta 1/2 lambda n, the last over here. So this is like delta 1/2 lambda n, which is, if you plug in what delta 1/2 lambda n is, delta 1/2 cancels with this one. So I see exactly second derivative of u, the starting max times k to the power n. Okay. So what I want you to realize is because, okay, I always, so the worst part in these errors contains the second derivative of the map which you are perturbing. This map is constructed as by adding a perturbation which is highly oscillating with parameter lambda I minus 1. So the worst over here is delta 1/2 or delta, because I'm getting another delta 1/2. And then I see previous frequency divided by the actual frequency, which frequency of the present oscillation. So because of this, if I want to achieve a decrease of my metric error of some fraction k, I just need to choose my frequencies iteratively, just increasing them by a factor k. Increasing for every step, I need to increase a factor k, such that in the end, to get a decrease of the metric defect, so delta is the defect of g minus u star e. So I'm starting with u, it's delta far away from g. I want a v which is delta divided by k far away from g. To achieve this, I choose my lambdas. I choose my lambdas to achieve this, and I see that my second derivative increases by a factor k to the n, where n is exactly the number of spirals I need to add.
This makes geometric sense if we think that, like Colin said in the previous talk, if we think of the second derivative as curvature, right? So you're wrinkling more of the
Definitely, yeah.
So the curvature is
more definitely. This is our kind of quantitative or very heuristic sketch of a quantitative stage proposition, which tells you that if you want to decrease by a factor k, you can do it at the expense of an increase of the second derivative of order k to the n. So decrease in this method by factor k. Or decreasing leads to increase of second derivatives. Of further or by factor k to the power n, where n is the number of primitive metrics in the decomposition. Or more precisely, it's actually not the number of primitive metrics in the decomposition, but it's the number of spirals at different frequencies which we need to add. Of spirals of different oscillating at different frequencies. We need to add it. Okay. Now let's see what this gives us. So now instead of saying, okay, my second derivatives, they go to plus infinity, they blow up. I know exactly how fast they're blowing up. They're blowing up in this rate k to the n, whereas the induced metric, it decreases by this factor k. Okay, so what does this imply? So it implies that when I iterate this stage proposition, which I just sketched you, it means that I can construct a sequence of short maps UK, such that my induced metric over here is delta divided by k to the k. Okay, let's take another. No, let's take k. Iterating a proposition means that we can construct a sequence of strictly short maps, UK, such that induced metric less than or equal to delta to the k minus k. Just decrease every time I decrease by a factor k. Small k. The first derivatives. So this one is like, so yesterday, the same as yesterday. This can be estimated by g minus uk minus 1, 0, 1/2. This is from yesterday. First derivative doesn't go any further than how close I am to g already. And if I look over here, this can be estimated by delta 1/2, and then k, the minus k minus 1, 1/2. Okay, and delta is d minus the initial coordinate. And now my second derivatives. I just estimated like by the sum. So this is less than or equal to the sum. And I know that when I go from uk minus 1 to uk, I'm losing exactly k to the n over here. So this is less than or equal to delta uk minus 1, 0, 1 plus, and then I'm losing this factor k to the n. Okay, so this is, and now, sorry. Yeah, and then here I'm losing the factor k to the n again, so this is less k to the n. That's cool. So on. So that I know that the worst part is, so I get a k to the kn, the d to 0, and then I get a k to the n times k. So, okay. I mean, up to 2 or something. Up to this. So what does this tell us? Well, now we know that this guy is going to 0 geometrically. This guy is going to plus infinity with a certain rate. So somehow putting an alpha over here and gaining something over there, we might hope that in fact we're converging. And this is just recall. So if I want to compute the C0 alpha norm of the first derivatives, okay, I want to show that this sequence over here converges in C1 alpha for some alpha. I have an estimate on the distance between the C1 norms. I have an estimate between the distances of the C2 norms. So the C1 alpha norm lies somewhere in between. So this is interpolation. So recall, observe that if you have a function, alpha between 0 and 1, what is the Hölder norm? Like the Hölder semi-norm, it's simply the sup over x unequal y of x, f of x minus f of y, divided by x minus y to the alpha. It's by definition the Hölder semi-norm. And now you just realize that, okay, rewrite it as f of x minus y, f of y divided by x minus y, and the whole thing to the alpha, and then multiply f of x minus f of y, 1 minus 1. And you see that in order to estimate a C alpha norm, or C alpha semi-norm, it suffices to estimate the C1 norm of f. So this can be estimated just by intermediate value theorem, or this is like the Lipschitz norm of f to the alpha. And here I take twice the supremum norm of f to the 1 over alpha. So this is less than or equal to the C1, or if you add 0 to the alpha. And then here is twice f C0 norm 1 minus alpha. That is to say, if I want to check whether I have convergence in C alpha, I can just look at how fast the second derivatives are growing. Okay. I want to apply this to f being the first derivative of my sequence. I see I just need to check how fast the second derivatives are growing, put an alpha over there, put a 1 minus alpha in the first derivatives. So if alpha is very small, this is very close to the C0 norm. I need just some little piece of the second derivative. Alpha is very large, and I need more of the first derivative. So hence, duk minus duk minus 1 in C0 alpha is less than or equal to the constant which depends on alpha, like 2 to the 1 minus alpha. And then duk minus 1 in C0 to the alpha, to the 1 minus alpha. And then d squared uk minus d squared uk minus 1 to the alpha. Okay? Just applying this estimate. And now I have the exact estimates of what these guys, or how large these two guys are. Right? I know how far I'm going in C1. It's exactly delta 1/2 times this factor. So this is less than or equal to delta and then 1/2 1 minus alpha. I don't care because it's some constant. But let me still write it. And then I have this factor which decreases. So I get k to the minus 1/2 k minus 1, and then I get this power, 1 minus alpha. This is just, all of this is the 1 minus alpha power of this estimate. And the second derivative over here, I get a d square u0 to the alpha, and then I get this factor k to the n k alpha. And okay, I want to send k to plus infinity, so what I really need to check is what happens to these terms with the k. So let me, we're almost done, sorry. Okay, so this is the same as some constants, constant depending on delta, depending on u0. Just this one, also an alpha, I don't care. And then k to the minus 1/2. And let me put the k over here, k to the k. Then I have n times alpha. And then I have minus 1/2 times 1 minus alpha. And then, okay, I get something from the 1 over here. K to the,
It's not touching the part of the 1, it's just a constant.
it's just a constant.
Yeah.
Just, so this is 1/2 1 minus alpha. I don't care so much. So this is not going anywhere with k, but this is going anywhere, somewhere with k. So to see that this is a sequence which is converging in C alpha, I want to say that this is a summable sequence over here. And to say that this is a summable sequence, I just want that this exponent over here is negative. So converging C1 alpha if n alpha minus 1/2 1 minus alpha is less than 0. This exponent over here, which is multiplied by the k. Okay, and this means, I mean, you can do the computation, alpha is less than 1 over 1 plus 2 times n. So I'm getting a Höhler exponent over there. I get convergence in C1 alpha with an exponent which depends on how many spirals I need to add at in every stage. So you can show, or you can set up the scheme such that, remember, in the second lecture, I showed you the decomposition lemma of Nash, which showed you that locally you can decompose any metric in exactly n star primitive metrics. So where this one was exactly the dimension of the space of symmetric matrices and bimatrices. So you can set up the scheme such that in the decomposition you don't get a big n, but you always get this smallest number possible, such that n is exactly n times n is 1 divided by 2. And this gives you exactly Borzo's exponent. Plugging this n over here, you see the 1 over 1 plus n times n plus 1.
Borisov did not have the idea, so he's working with analytic metrics, but he doesn't have the idea of smoothing.
Yeah.
But like Nash-Moser was already around when, like, I mean, Moser kind of came up with the idea. It had been there from the 1960s and 70s.
Yeah, I don't know. Why not?
Interesting.
Okay. So in the last couple of minutes, let me show you how to get better exponents, or like how we could hope to get better exponents. And then closing this. So how to get better exponent? Well, one obvious thing to try is to reduce n. Reduce the number of primitive metrics needed in the decomposition. It's it's not easy. And in fact, in 2 dimensions, it's really possible, because in 2 dimensions, you have a nice coordinate transformations. So for 2-dimensional Riemannian manifolds, you have a good choice of coordinates, isothermal coordinates or conformal coordinates, which diagonalize your metric. So instead of decomposing, this one into 3 pieces, like for n equals 2, you would get 3 primitive metrics. You just choose a nice coordinate, choose nice coordinates on this Riemannian manifold with this with this Riemannian metric, such that this is diagonal. Then you have only 2 terms. You have a diagonal metric, 2 primitive metrics, and so you get a 2 over here. This is your 1 over 5. So first thing, reduce n. And in fact, in my work with Lelis, coming off myself in Glasgow 2018, to use conformal coordinates to diagonalize. Minus in 2. So this applies n equals 2, and you get alpha. Let's see. Of course, now you introduce a coordinate change. This introduces more errors, so it's not at all trivial. As I said, n is the number of primitive metrics, or more precisely, the number of spirals at different frequencies, which you need to add. So what you can do is just increase the codimension. Increasing the codimension allows you to add spirals at the same time. And all these spirals at the same time, you can choose the same frequency. So you don't need to choose lambda I is lambda I minus 1 times k, n times, but essentially n divided by the codimension time. So you choose, so if you have codimension, let's say k, you go from Rn, so increase codimension. You go from n dimension into Rn plus k. You can add k spirals at the same time. roughly speaking, you need only n divided by k, so n star divided by k spirals at different speeds. And so you get this number alpha less than 1 over 1 plus 2 n star over k. Okay, and two more things. So here it seems that if you're if k is 2 n star, this one is 1, so you get 2 1/2. So here for k is n star, this gives alpha less than 1 over 2. Your favorite maybe critical exponent, but with a very high codimension. So we're going into the space n plus n star. There is a work by Kellen where he shows, I mean, he chooses a much different codimension, but his work, wait, 2 n star, sorry. But you can show that his work also works if the codimension is only 2 n stars. But let me just say this because it's a very genius idea, I would say, or it's not too far, this idea, but it's still not easy to make work. So if k large, Helen in
What's of the 78, I don't know.
70 as a different idea, which works for k bigger than or equal to 2 n star. So q is bigger than or equal to n plus 2 n star. And the idea is very simple. Instead of decomposing the metric error at the k step, or no, let me say the ith step. So what we did is decompose this guy into a number of primitive metrics. Let me not put n star over here. So we did this decomposition, we added the spirals, and what we ended up with was what the map B, such that we have this one, plus all the primitive metrics, plus the errors. So just doing our thing, we got this one. Adding n spirals, we got the primitive metrics plus these errors. And then we said, okay, this one is simply g minus u, e. And I get g up to these errors. And now what Canon does is say, well, instead of only saying this is this piece, let me just incorporate these guys into the decomposition. So add all the errors over here. Because then all of this is g minus u at play. And you almost have no errors. I mean, if this worked 100%, then you would just get it in one piece. The problem is these guys, they depend on derivatives of A. So this is not at all easy. So this assumes, so O1 over lambda L depends, so let me kill this, depends on derivatives of A, L, this is not easy. So the question is, given this one, find appropriate ALs, such that not only this one is equal to what I've given, but also these terms with the derivatives of AI inside. Yeah. So somehow needs a very so it seems like an implicit function theorem, but because these also depend on the derivatives of AL, it's much more difficult. So you need to run some sort of Picard iteration, and you can do this up to an error which is as small as you want. And okay, here I forgot, instead of lambda L, in fact, because K is so large, we only have one frequency. You add all of the spirals at the same time. Right, we have n star spirals, we have two n codimensions, you could choose two n. So you can do this decomposition over here up to an error which is of order 1 over lambda to the power, to some power big M, and you can choose any M. And doing this, you get C11. Alpha less than 1. Helen gets to C11. And let me end with following. If you increase the codimension even more, Government said it already before. You have the works by Nash, the 65 paper. 56. 56 paper. So this one. If K is even larger, with Nash 56, which tells you that if G is CK, then you can find a CK embedding, or I call it V.
I think you're overusing the K.
And let me end with the sketch of regularity. It's kind of a summary. So here's the regularity of my G. Here's the regularity of the isometric embedding, which I can construct. So here we have 1, here we have 2, here we have 1, here we have 2. And so over here, I'm sitting with Nash. So this one is Nash. If C0 metric, I get a C1 embedding. If I'm bigger than 2, okay, this is actually Jakobowitz. So if I'm bigger than 2, let me be more precise. You can do J alpha, where J plus alpha is bigger than 2. So if you're at J alpha, you have a nice increase over here. So this is Nash 56, or this version with J alpha going to J alpha is, I think, Jakobowitz. So given a metric which is C J alpha for J plus alpha bigger than 2, you get an isometric embedding. So all of this is if K large enough. This is a picture for the high codimension case, high regularity case. And then inside over here you have Kellen. So this is basically Kellen. In 70s. It tells you that if the metric is Cj plus alpha, you can get, in fact, a U, which is Cj plus alpha halves. So in particular, U is, if G is C2, then you get almost C11. Okay, and here, this is another problem. So this is what Gromov calls the outrageous conjecture. So it's not known even if K is super large, whether given a C2 metric, you can find a C2 in general. Okay, so this is the picture for a large codimension. And with this, I think I want to stop because I'm way over time.
No, I think
It's exactly right.
Yeah, exactly right.
okay.
Yeah, sorry for being a bit technical, maybe in the last talk, but I wanted to show you how this exponent turns up. What are the challenges? How you might hope to get better exponents? Where we are in terms of the threshold problem. And also, so I should mention that our work, which I stated at the very end, these are the techniques or the obvious techniques on increasing the regularity beyond Borisov's exponents, like reducing n, increasing codimension. So what we do in the paper, which I mentioned at the end, we are in codimension 1, so we cannot increase codimension. This one is not feasible if you don't have high codimension. So we are not technically, not really absorbing error terms into the decomposition, and we're not reducing n in the decomposition. So we have different techniques which allow us to go past this exponent and get, in particular, the 1/3 for 2 dimensions. But I think would require another several talks to talk about this. But I hope you got an insight or a glimpse into the analysis side of these very powerful iteration techniques invented by Nash and powerful theorems which were proven by these techniques. And I hope the probability piece by Dominik gave a nice compensation to these more analysis-focused talks and give somehow a rounder or complete view of these problems. So thanks very much for sticking around.
Questions? For Dominik, questions?
Just one. So just n equals to 2 allows you to decrease n.
Yeah.
Just n. Yeah. Just that. Just that. All the rest, the optimal should be n star. Okay.
Yes. This. I don't know of any coordinate transform which does this in higher. Which kind of diagonalizes or in some sense gets rid of more than a couple of primitive metrics over here in general dimensions. So for n equals 2, you have this nice coordinate change such that you really have a diagonal matrix with positive entries. And in higher dimensions, in some cases it's true. You have these characteristic classes. I think Stiefel-Whitney classes or Whitney tensor. If this is 0, then you find some coordinate change, but you would have to guarantee that the Whitney tensor for at every point for this metric is 0 to kind of diagonalize in this case, and this is just not feasible. Maybe you can control it at the beginning, but then along the iteration, I don't see a way. And so what we do in this paper I just mentioned, at the end, somehow we get rid of n pieces. So the exponent I gave you was 1 plus 1/1 plus n times n minus 1. And so this is exactly 1/1 plus 2, and then n star minus n. So we basically get rid of n perturbations to add. It's like the first row. Yeah, whatever. Sorry.
More questions? No?
So it's possible, or it has any sense that use conformal coordinates to analyze or construct short maps? Or maybe what is the relationship between conformal coordinates and short maps?
I don't really know how to answer this. The fact that we're a short map allows us to choose conformal coordinates with respect to this, because then this is a metric, Riemannian metric. But at any stage, choosing conformal map, conformal coordinates exist for a Riemannian metric. Because we're short, this is a Riemannian metric very high. So because of the shortness, we can choose conformal coordinates for this metric over here, the metric defect. But using conformal coordinates to construct short maps, is this your question?
Yeah.
I wouldn't know how to do this, but it's a good question.
More questions? Okay, we thank Dominik and